Imagine the universe, a vast expanse filled with countless stars, planets, and galaxies, each with its own unique story and structure. Now imagine it inside your computer, a digital cosmos where data flows like stardust, creating intricate patterns and connections. It sounds like science fiction, but in a way, it's true. Your computer is a universe of its own, with data acting as the stars and planets. Data structures are the constellations of this digital universe. They map out the pathways and connections, guiding the flow of information. They are the invisible frameworks that hold and organize data, much like the gravitational forces that shape galaxies. Without them, our computers would be lost in a chaotic void of information, unable to make sense of the vast amounts of data they process. Just as stars cluster into galaxies, data organizes itself into structures. These structures bring order to the digital chaos. These structures determine how data is stored, accessed, and manipulated. They are the backbone of efficient data management. From the simplest app to the most complex algorithm, data structures are the fundamental building blocks of software. They enable functionality and performance. Understanding data structures is essential for any aspiring programmer. It's the foundation upon which all software is built. It's like knowing the constellations before embarking on a journey through space. This knowledge provides direction and clarity. With this knowledge, you can navigate the vast expanse of data and build powerful, efficient applications. You become the architect of your own digital universe. So buckle up, space cadets. Prepare yourselves for an exciting journey. We're about to embark on a journey to explore the fascinating world of data structures. Get ready to unlock the secrets of the digital cosmos. Before we can explore the cosmos of data structures, we need to understand the language of data itself. Data is the foundation upon which all digital information is built, and it comes in many forms. Data can be anything: numbers, text, images, sounds. Each type of data has its own unique characteristics and uses. It's the raw material of the digital age. Just as raw materials like wood, metal, and plastic are used to build physical objects, data is used to build digital experiences and applications. A data structure is like a container for this raw material. It provides a way to store, organize, and manage data efficiently. It provides a specific way to organize and access data. Without proper organization, data can become chaotic and difficult to manage. Think of it like a library. A well-organized library makes it easy to find the information you need quickly and efficiently. You wouldn't just throw books onto shelves randomly. Doing so would make it nearly impossible to find a specific book when you need it. You'd organize them by genre, author, or title. This systematic arrangement helps in quick retrieval and efficient use of resources. This makes it much easier to find the book you're looking for. Similarly, a well-chosen data structure makes it easier to access and manipulate data. Similarly, different data structures offer different ways of organizing data. Each structure has its own strengths and weaknesses. Some structures are linear, like a queue at a supermarket. In a queue, each item is processed in the order it arrives. Others are nonlinear, like a family tree. These structures allow for more complex relationships between data elements. The choice of data structure depends on the specific task at hand. Different tasks require different ways of organizing and accessing data. Just as a carpenter chooses the right tool for the job, a programmer must choose the right data structure for the task. The right choice can make a significant difference in the efficiency and performance of a program. Choosing the wrong structure can lead to inefficient code and slow performance. This can result in wasted time and resources and a poor user experience. Let's start our exploration with one of the simplest and most fundamental data structures, the array. Imagine a row of lockers, each with a unique number. This is essentially what an array is, a contiguous block of memory locations, each storing a single piece of data. Arrays are all about order. Each element in an array has a specific index, which determines its position. This makes accessing individual elements very fast. You simply need to know the index of the element you want. However, arrays have their limitations. They are static structures, meaning their size is fixed once they are created. Adding or removing elements from the middle of an array can be a time-consuming operation. Despite these limitations, arrays are incredibly versatile. They are used in countless applications, from storing lists of items to representing matrices in mathematical operations. While arrays provide order, linked lists offer flexibility. Arrays are like neatly organized shelves in a library where each book has a specific place. But what if you need to insert a new book in the middle? You'd have to shift everything around. That's where linked lists come in. Imagine a chain of stars, each connected to the next. This is the essence of a linked list, a dynamic data structure where each element, called a node, points to the next node in the sequence. Unlike arrays, which require contiguous memory allocation, linked lists don't need to be stored in a continuous block of memory. This means they can grow or shrink easily as needed. You can add or remove elements without worrying about shifting everything else around. Adding or removing elements is as simple as adjusting the pointers between nodes. However, this flexibility comes at a cost. Accessing a specific element in a linked list requires traversing the list from the beginning until you find the desired element. This can be slower than accessing an element in an array, especially for large lists. Imagine having to walk through a long chain to find a specific link. Despite this, linked lists are ideal for situations where the size of the data is unknown or changes frequently. They offer a level of flexibility that arrays simply can't match. For example, in applications like memory management, music players, and implementing undo-redo functionality, linked lists shine. They allow for efficient memory use and dynamic data handling, making them a powerful tool in the data cosmos. So whether you're managing memory, creating a playlist, or implementing an undo feature, linked lists provide the flexibility and efficiency needed to navigate the ever-changing data landscape. Stacks and queues. First in, first out, sometimes. Stacks and queues are like specialized versions of linked lists. They enforce a specific order of data access. Imagine a stack of plates. You can only add or remove plates from the top. This is the principle of a stack, a last in, first out structure. Queues, on the other hand, are like a line at a ticket counter. The first person in line is the first person served. This is the principle of a queue, a first in, first out structure. Stacks are used in applications like function call management, expression evaluation, and backtracking algorithms. Queues are used in scenarios like handling requests, scheduling tasks, and buffering data streams. Trees, branching out for efficient searches. Trees introduce a hierarchical structure to our data cosmos. Imagine a family tree branching out from ancestors to descendants. This is the essence of a tree data structure, a non-linear structure with a root node and branches of child nodes. Trees are particularly well suited for searching and sorting data. Binary search trees, for example, allow for efficient searching and insertion of data. Each node in a binary search tree has at most 2 children, ensuring a balanced structure that facilitates fast search operations. Trees are used in a wide range of applications, including file systems, databases, and representing hierarchical relationships in data. They are an essential tool for managing and manipulating complex data structures. Choosing your cosmic structure. With so many data structures to choose from, how do you know which one is right for your needs? The key is to consider the specific requirements of your application. What operations will you be performing most frequently? How important is speed of access? What is the expected size of your data? Answering these questions will guide you towards the most appropriate data structure. For example, if you need to store a fixed number of elements and access them quickly by index, an array would be a suitable choice. If you need to add and remove elements frequently from the middle of the structure, a linked list would be a better option. Choosing the right data structure can significantly impact the performance and efficiency of your code. It's like choosing the right spaceship for your interstellar mission. Data structures in the real world. Data structures are not just abstract concepts confined to textbooks. They are the invisible forces that power our digital world. Consider the internet. Web pages are linked together in a vast network, much like a linked list. Search engines use sophisticated algorithms that rely on trees to index and search billions of web pages. Social media platforms use graphs to represent relationships between users. GPS navigation systems use graphs to find the shortest route between 2 points. From online shopping to video streaming, data structures are at the heart of it all. Understanding data structures gives you a glimpse into the inner workings of the digital world. It's like having a backstage pass to the greatest show in the universe, the intricate dance of data that shapes our lives. The ever-expanding universe of data. The universe of data is constantly expanding. New technologies and applications are emerging, demanding ever more sophisticated ways to manage and manipulate data. As we venture further into the digital age, the importance of data structures will only continue to grow. Mastering data structures is not just about writing efficient code. It's about understanding the fundamental principles that govern the flow of information in our increasingly digital world. So keep exploring, keep learning, and keep pushing the boundaries of what's possible with data. The universe of data is vast and full of wonders, waiting to be discovered. If you learned something new, like the video, share your thoughts in comment section, and don't forget to subscribe the channel for more related videos.